Hello, good morning. Here it's Gianpietro Cagnoli, and welcome to this short introduction to the thermal noise problem on gravitational waves. You will see that in this registration there will be a lot of sections, okay? Because we're going to touch several arguments, and I hope to be clear. And in any case, we're going to have the question and answer session. And also, you can send me emails if later on you want to ask me something. So my email is this one. So I'm going to start to see what is the layout of a typical gravitational wave detectors and how to calculate at the beginning the thermal noise and what is the impact of thermal noise on the detector. So let's start. I share the screen. Here it is. Okay, that's right. So this is a typical layout of a gravitational wave detector. So you see here the laser, the mode cleaner, and then the input optics, the power recycling mirror, there's a beam splitter, and this is a typical configuration of a Michelson interferometer, but there is a cavities, Fabry-Perot cavities in the arms. And then there is the output, the output system that analyze the light and produce the signal, the electrical signal of the detector. So the first question that somebody could have is, well, how is possible to calculate the thermal noise of such complicated device like a gravitational wave detector? Well, there is a way to simplify greatly the problem, because thermal noise is just a noise that acts on. We should calculate any displacement noise of all the components, but in reality, we will see that this is not the case for two reasons. So first, what we are going to see now is here in the next slides is the sensitivity of the displacement sensitivity of a Fabry-Perot cavity. So it means what is the response of a Fabry-Perot cavity to a solicitation made of a displacement of mirrors. Okay, so in this case, we can imagine to displace either the input mirror or the end mirror. What we're going to change is the length L of the cavity here. This is the length is given in terms of wavelength of light. So 0 is an artificial 0, so it's something is a length that is a multiple of the wavelength. And on the y-axis, we'll see the phase of the light that is reflected back from the cavity. So if there is no Fabry-Perot cavity in the arm, the the relation between the face reflected back and the length of the cavity, that in this case, since the cavity is not there, is practically the distance of the mirror at the far end of the arm, is just a linear function, okay? Because every time that we, for example, we displace the end mirror of 1 millimeter, the light has to travel 2 millimeters, okay? So in fact, the relation between the phase and the length is simply 2k. K is the wave number of the light times times L. Okay, L is the distance of the mirror at the end. When instead, when we use the Fabry-Perot cavity, here we'll see that this function is no longer linear. Is made by plateau, in which there is the sensitivity of the phase reflected back from the cavity goes down to 0. Also, there are regions where the sensitivity increases a lot. Like, for example, here we have at 0, at half wavelength, plus and minus, okay? So in this case, and these are the conditions where the Fabry-Perot cavity is in resonance. So you will see that here, this is the reason why we are using the Fabry-Perot cavity. Here, the sensitivity increases a lot, okay? So it means that you will not gain simply by double the path length of 2 every time one of the 2 mirrors is increasing or reducing the length of the cavity. But you gain a factor that is proportional to the finesse of the cavity, okay? As a matter of fact, you can take the gain in the phase sensitivity like the finesse. So in practical terms, you should calculate what is the equivalent number of bouncing that the light goes up and down in the cavity, and this number is proportional to the finesse, is close to the finesse, and then you have to multiply this by 2k, okay, and this will give you the sensitivity of the cavity. So this it's really nice for us because it means that not all the thermal noises, and we'll go back to the previous slides on the detector, not all the thermal noise, mechanical thermal noise, so not all the displacement of all the optical components in the interferometer are weighted in the same way. If we imagine that the mirrors are made almost with the same technology, we can imagine that the thermal noise is almost the same or so in all the optical components. But due to the amplification of the Fabry-Perot cavity, the only thermal noise that matters in a gravitational wave detectors is the thermal noise that is affecting the main mirrors. And the main mirrors are the mirrors of the 2 Fabry-Perot cavities, the input and the end mirrors of the cavity. So therefore, so now we can stop sharing the screen, so we can start to write down something, because it's really important for the calculation of the impact of thermal noise on a gravitational wave detector. So, as we said, there are just 4 mirrors that matters. Okay, so we can imagine that each mirrors produces a power spectral density of noise as XX is a function of omega in each of the four mirrors. So I restart. So here SXX is the power spectral density that characterizes each of the mirrors. So at the moment, we are, let's not do this assumption. So there will be 4 mirrors. So we are going to have 4 of this spectral noise density. So this is the index I will tell us which of the mirrors. So we're going to imagine that each of the mirrors are independent from the other. So we are allowed to sum in quadrature all the noises. And this is already, this is the power spectral density of the noise. So this is already an information that is in quadrature. So each cavity, okay, the noise on the length of the cavity, okay, it will be the sum from I1 to 2 of the displacement noise in each in each mirror, okay? And so this is the noise associated to this cavity. An equivalent noise will be there, so SLL prime will be I from 3 to 4 SXX I omega, okay? So the total noise of length is the sum of these two, okay? So SLL total is the sum I1 to 4 SXX I omega. Okay, so this is the noise, the spectral density of the noise associated to the length of the cavity. Okay, so now we should understand how we are measuring the gravitational wave amplitude h. So we should remember that if we are considering the reference frame of the laboratory, of the Fermi, what is called the Fermi reference frame. So each mass is subjected to a force, okay, that make the displacement of the mirror. So this force in the the displacement that is consequence of the effect of gravitational wave is proportional to the distance of the object with respect to the observer. The observer, in this case, we can imagine that is here located on the beam splitter. The two input mirrors are really close. They are about 10, 20 meters from the beam splitter, whereas the end mirrors are, for example, in the case of LIGO India, is 4 kilometers. So it means that the effect of gravitational wave on the end mirrors is about 40 times higher than the effect of the input mirrors. So therefore, here we are considering the displacement only on the end mirror of the cavity. So here the cavity, for example, in the polarization plus the length here changes by half h plus the length of the cavity, so the distance of this mirror with respect to the beam splitter. And here it changes by the opposite, so half, well, the opposite, the opposite half h plus L. So it means that the interferometer will read the differential changes of the arm length. So practically the delta L produced by the total delta L produced by the gravitational waves is just h plus times L. So therefore, it will be really easy to convert this displacement noise into the equivalent noise of on gravitational wave amplitude. So SH total is simply SLL total divided by the length of the arm. Okay, so here at least we're going to have a simple way how to convert how to relate the displacement noise in each of the mirror to the equivalent noise on H. So the dimensional unit of SLL is meter square per hertz. And here, yes, definitely. Sorry about here we are talking about power spectral density. So here I have to put a square, okay, because this is the power, okay. So therefore, the spectral density on H is just 1 over hertz, okay? Because the dimensional unit of H is 0, okay? Is a strain of the space, okay? So therefore here, in fact, let's see what is the amplitude, a typical spectrum of noise of a gravitational wave. So, okay, so let's say. So I'm going to share the screen again. Okay. So here you can see a typical sensitivity curve, what is called sensitivity curve of gravitational wave detectors. In this case, the detector is advanced Virgo Plus, okay? And you will see that on top of the theoretical curves of different noises, we have also the actual curve that was taken at the beginning of the observation time 3. Okay. So here there are different components of the noise. So first, the graph presents on the y-axis the strain noise. So this is the noise in terms of equivalent amplitude of gravitational wave. On the x-axis, you have the frequency. Maybe later on we are talking about why the power spectral density is given in this unity. Well, the strain is exactly the square root of the power spectral density of the noise that you calculate or you measure on H. So the power spectral density on H has the dimension 1 over hertz. So the amplitude spectral noise is just the square root of it. So you will see that there are different components of noise. Not all the noise are fundamental. There are some technical noise, like for example, this line that for advanced Virgo represents the major contribution to the limit to the sensitivity of the detector. Today, we are discussing the thermal noise contribution. So the thermal noise that comes from coatings. And Professor Reed will talk extensively on this thermal noise. So here we are introducing in general the subject. And also there is also the other component of thermal noise, which is the suspension thermal noise. Once the technical noise are solved, at the low frequency, the sensitivity is limited by thermal noise and Newtonian gravity gradient noise on a detector. So this is our two noise contribution. So let's see, I stopped the sharing the screen because I add some more information about these two noises. So general characteristic of this noise, okay? So this is the logarithm of frequency, and here you have the square root of SHH. Okay, so this is the amplitude spectral density plotted against the logarithm of frequency. So the two thermal noise contribution has so the thermal noise that comes from the coatings of the mirrors has a typical shape like this. So in this log-log plot, well, is a straight line with a slope of just half. So this is f to the minus 1 over 2. Okay. So there is the other thermal noise, the suspension thermal noise. This is not the case in real life, but in general. So when you have not a too complicated system, the function is f to the minus 5 over 2. Okay. Then, especially for the suspension thermal noise, or not especially, for example, in the plots that I have shown you before, this is not the case. It's a more complicated function. But in general, is simply f to the minus f5 over 2. So we're going to talk exactly why it is so, and there is some physics behind it. And this is the purpose of this short course on thermal noise is just to help you to calculate thermal noise easily, okay, with some easy, let's call it easy calculations, okay, and and to derive why the two main components of thermal noise are in that way. So, first of all, it's kind of strange that there are two components. I talked to you that there's just one, there are 4 mirrors. I said that there is a displacement noise in each mirror. So why now there are 2 thermal noise for the same object, for the same components of the detector? Well, this is kind of a simplification, okay? So this is just a mental idea that will help us to calculate in an easier way thermal noise. In reality, there is just one thermal noise for each mirror, okay? But then we make the things in a way that, well, we identify different components of the thermal noise for each test masses, okay? So as the word says, the suspension thermal noise is the thermal noise that is due to the fact that there are fibers holding the mirrors, suspending the mirrors, okay? And this is coating thermal noise it means that there is a thermal noise associated to the films that we deposited on the mirrors in order to make the surface reflective. Okay. So let's start from this, and also there is something else that is not present in this plot, is the thermal noise that comes from the substrate, okay, from the substrate of the mirror. So as a Professor Reed will tell you, most of the thermal noise that comes from the mirror itself, it comes from this films, these thin films that we deposited to make the surface reflective, and not from the substrate. Even if the substrate is 20 centimeter thick, there's less thermal noise on this that comes from the substrate than that comes from the coatings. So, what is this thermal noise? So the thermal noise practically is it's something that is. I stop this. Okay, so where does it come from? This the thermal noise. Well, an explanation, a fundamental explanation, you can find it in the Landau-Lifshitz book on statistical physics, and I'll share with you the one page that gives us some very important hint. So what is the idea? We take a system. In our case, is for example, is a bunch of material that is making the mirrors. So this we call it our system, is placed in an environment, okay, and our system is in connection with this environment. The environment, we can call it the thermal bath, okay, of the system. So since we consider the system from the point of view of statistical physics. So there are, since we are in statistical physics, the fundamental quantities of this system that is not isolated are continuously fluctuating, okay? Because the realization, so what we call it, the actual shape, temperature, and whatever other characteristic of the system, these are just the most probable quantities that are present in our little system. Here in the Landau-Lifshitz book, for example, the authors are calculating what is the magnitude of fluctuation related to two variables. Here, the variables that they are considering, and they're quite important for us, are the temperature and the volume. Okay, so temperature and the volume are fluctuating because the temperature practically is the energy, is the mean energy of our system. Since our system is not isolated, our system can give and take energy from the environment. So definitely the temperature is not constant, but also the volume, okay? Also the volume, or if we fix the volume, the number of particles that are occupying a certain amount of volume on the space is fluctuating because the system is not isolated, okay? So these two quantities, the the temperature and the volume fluctuates, okay? And the first equation, the 112.5, it tells us that the average of the product of these two fluctuations is zero. So it means that the fluctuation of temperature and the volume are completely uncorrelated, okay? There are independent fluctuations of these two quantities. And so it means that, for example, what is changing in the volume? Practically, it changes the shape, for example. The shape of our material is changing constantly. So definitely, now you understand the importance for the detection of gravitational waves, okay? So if the shape of our mirrors is changing, and each part of the mirrors changes its shape, so definitely, this is a really dangerous, or dangerous. I mean, it could impact, could limit the detection of gravitational waves. So, and look at the following equation, number 6 and number 7. So, number 6 and number 7 are telling us how much is the amplitude of this fluctuation. So, the average value of the square of the fluctuations, okay? So the variance. So the first equation, it tells that delta t square on average is K is the Boltzmann constant, T square divided by the heat capacity of the material, okay? So the heat capacity of the material in this case is a quantity that depends on the amount of material that we consider, okay? So the smallest is the amount of material, the smallest is CV, so the higher is the fluctuations in temperature. And the second equation is telling us what is the amount of, what is the magnitude of the fluctuation in volume. So in this case, the square of it is proportional to the temperature. Also, it is also proportional to the, well, we can call it the yielding of the material, or is inversely proportional to the volumetric stiffness of the material. So it means that the more rigid the material is, the less is the total fluctuation, the amount of fluctuation in the volume. So here we're going to see, we start to see a bit of what are the important parameters in all this business of thermal noise. So first, you will see that temperature is important. Okay, definitely when the temperature goes down, all the fluctuation in temperature and the volume decreases. Then for the thermal fluctuations, it's important the volume, okay, of the material. The larger, the better. But don't be fooled by this, because in the mirror there are regions that are not connected for what regards temperature fluctuation, because if the two regions are too far, by the time that the gravitational wave is passing through, there is no possibility to make the temperature homogeneous. Okay, so you cannot decide, well, I make the mirror really large, and so the thermal fluctuations are small. Yes, for the whole mirror, but there are different volumes inside the mirrors that are not that are uncorrelated from the point of view of temperature fluctuations. So in the second, volume fluctuations are limited definitely by reducing the temperature, but also are limited by the fact that we can choose a material that is really rigid, or other techniques that makes the system mechanically rigid. Okay, so these are kind of two important relations, because it gives us a very fundamental origin of thermal noise. Okay, so I stop the sharing here. So I'm going to copy the two results that we have seen. So delta t squared, on average, this is a K of Boltzmann t squared divided by the heat capacity at constant volume. Okay, and the other is the delta V squared. So this is minus T, the temperature, by dP over dV, which is the volumetric rigidity. Okay, so normally this is negative. Okay, so therefore the fact that normally in all the material this is negative, so it takes out the negative that we have here. So this quantity definitely is becoming positive. Okay, so it is clearly important, this contribution of thermal noise, because if we have our mirror with the two fibers, if for each of the volumes that are here in all the system, we apply this relation, we will see that the position on space of the mirrors, but also the shape of the mirror is changing. So definitely this is coupled directly to the output of the detector. Okay. A bit more sophisticated is if, so the question is it important, the fluctuation of temperature itself in each of these little masses that make the mirror? Well, in reality, in general, is not important. So the detector is not sensitive to the fluctuation of temperature. We do not measure the temperature. But as you know, all the materials show the a thermal expansion. Okay, so therefore, every time in real material, every time we have a fluctuation of temperature, this is it produces a fluctuation of the volume. So what I want to say is that for each volume of the test masses, we have two independent origins of thermal noise. Thermal noise related to the fluctuation of the volume, okay? And in this case here, I want to point it out, this is calculated at constant temperature and fluctuation of temperature. Normally, this is the only thing that matters to us. But unfortunately, due to the fact that we are dealing with real materials, all the materials have a thermal expansion coefficient that is not zero. So in every temperature fluctuation is translated into volume changes. Okay? So therefore, we have, in practical terms, we have two sources of fundamental thermal noise. Okay? Volume fluctuations and temperature fluctuation. This is called a thermoelastic origin of noise. Okay, this is a thermoelastic effect. Once it is converted into volume displacement, and this is we are calling it structural thermal noise or Brownian thermal noise. Okay, Brownian from Brown, the Scottish botanist that first observed the motion of pollen in a water solution, and this is the first evidence that we consider this the first time that humans have detected thermal noise on a system, because normally thermal noise is something that is really small. So you need to have some device to see thermal noise. Okay, so structural or Brownian noise is independent fluctuation of volume. Every time the temperature fluctuations are converted into volume fluctuation, these are called thermoelastic effects that generate thermal noise. Okay, so now how to connect this to this? Well, you will see that there is really a big difference between these two approaches. Here, time and then frequency does not exist at all. So this accounts for the overall effect, okay, of thermal noise. And on top of this, if we want to calculate the overall effect of thermal noise, we are forced to take our system, divide it in small elements, and these small elements need to be separated. Okay, so what does it mean separated? We discussed before about the fact that two regions are not have a fluctuation of temperature that are not correlated. And this is kind of easy because heat does not propagate fast in glasses. So the region that are independent, that have an independent fluctuation of temperature in a mirror are quite small. Here is a bit more complicated because I mean the volume fluctuations propagates at the speed of sound. So here the calculations, if we want to calculate what is the overall effect of thermal noise from independent volume fluctuations, this is it's really complicated because here all parts of the test masses are connected. Okay, so this first is a very difficult problem to solve from a point of view of mathematics. But also there is a big difference because here we are calculating the distribution of the noise over the frequencies. So when we talk about frequency, there's time. Okay, here there's two equations. Time does not exist, like in statistical physics or in thermodynamics. Okay, so therefore, if the theory stops here, then we cannot do any progress at all. So there should be something else, some aid that help us to calculate the distribution of the thermal noise over the frequency. Otherwise, we are stuck. Okay, cannot calculate what is the impact of thermal noise on gravitational wave detector. So where does this information comes from? Well, it comes from a theorem that is called the fluctuation dissipation theorem that was established in 1951 by Cullen Walton. Okay, and is it is sometimes is called the generalized Nyquist theorem, because Nyquist and Johnson, well, they didn't work together, but Johnson were the years in the 20s. The first electronic amplifiers were produced. And so people soon recognized that there was some noise coming from electronics, and Johnson recognized that this noise came from the resistors. And then Nyquist did the calculation, demonstrated that effectively the noise, the power spectral density of noise, it was proportional of the resistance. And as a matter of fact, I don't know if you already have seen this expression. So if I have a resistance R, to each resistance, it is associated a voltage generator that is put in series, okay, to the resistance. And this is a generator of voltage that is random, okay? This is we use it to simulate the effect of thermal noise in electronics. And the expression of this generator, the amplitude of this generator, is kind of easy. It's 4 kBT times R. Okay. So the dimension of En is volt per square root of hertz. Okay. So this is called the Nyquist, Johnson-Nyquist expression of thermal noise. Okay. And in 1951, Cullen and Walton produces the generalization of this expression that is valid to, we can apply this formula to all the linear systems in thermal equilibrium. So no matter if we observe a current, voltage, displacement, temperature, it doesn't matter. Even this equation produces also the black body radiation, for example, because the black body radiation is practically the thermal noise of the electromagnetic field produced in an oven. Okay, the oven is made by a gazillion of atoms on the surface of the oven, and they are coupled with the electromagnetic waves. Okay, so and the radiation inside the oven, okay, is an expression of thermal noise. Okay, so I'm going now to talk about this theorem, the fluctuation dissipation theorem. Okay, so let's now talk about the fluctuation dissipation theorem, which is the major tool that we use to calculate these curves that I shown you before. Again, I'll share the screen, and we are going to see at a moment. I put back the Landau-Lifshitz book. So after Cullen and Walton did their original article, but if you read the articles, they are quite difficult, okay? So after the original articles, there were many translator, let's call it, of this theorem. The major translator of the fluctuation dissipation theorem is a Japanese scientist called Kubo, and so he explained a lot of things regarding the fluctuation dissipation theory. Well, there is also a nice resume of the fluctuation dissipation theorem in the Landau-Lifshitz book, Statistical Physics. Here in this edition, we are at the chapter 124, okay? And well, I copy immediately on the board the equation that represents the fluctuation dissipation theorem. So in our notation, so it means that S x omega, the power spectral density of the variable x that we want to know the thermal noise is well, this is a 2 h bar alpha second, which multiplies plus 1 over e to the h bar omega divided by kVt plus 1. Okay? Okay. So let's see. Let's comment it, and we'll see. Okay, I just stop the sharing, and I'll go to the board, and let's start to understand what are the quantities there. So this is the usual power spectral density of the observable x. So it means that we have our system. Our system that is a statistical system because it's made by virtually a large number of particles. Okay. We select one observable, so one physical quantity that we are interested at. This could be a mechanical quantity, like, for example, the component of the acceleration along one direction of one specific point of the system. So we have the system, and we observe this point, and then we want to calculate the noise associated to the acceleration in this direction. Or, for example, we are interested in calculating the temperature fluctuations of a region of this system. Or, for example, if this is our system, which is in a thermal bath, we want maybe we are interested to calculate which are the temperature fluctuation of all our system. We can we want to measure in this point, which is the noise associated to the electrical field in this direction. Okay, so x represent all this observable. Okay, you choose one and you calculate the thermal noise associated to it. Now you understand why this theorem is really important. So it gives you the freedom to calculate the fluctuation related to the fact that the system is at equilibrium temperature T in many circumstances. Okay, it's a very powerful theorem. So the power spectral density is 2 times h bar. So here, first hint that something is strange. So the theorem was derived considering quantum mechanics. which is an extension of classical physics. So now you understand why this theorem is also important. It's not just limited to the classical physics, but it considers the world physics. Then there is a function alpha, actually is alpha second, okay? This is called the susceptibility of the system. The information of the system is in there, okay? All the rest are just fundamental laws of statistical physics. But the information of the system is in alpha, okay? So we're assuming that the system is linear, otherwise the susceptibility doesn't have any sense, because if the system is not linear, the response cannot be expressed with a single function, because the response depends on the amplitude of the solicitation. Instead of in linear physics, the response is independent of the amplitude of the excitation. Okay. So what is alpha? Well, in the frequency domain, alpha is the constant that relates the response and the excitation. So the response is the variable x. The solicitation or the excitation. Well, at this variable x, it will correspond an excitation that we can call f, because if we are thinking to be in mechanics, okay, to the variable x that is in this case displacement, well, the corresponding excitation is the force. If we are not in the mechanics, how to find the proper excitation to the variable, to the observable that we choose? Well, there is one rule. The product of the response and the excitation must be always an energy. Okay, this is a kind of a very important rule. Okay, because the product x times f should represent the external interaction that you add in the Hamiltonian of the free system. So you have the Hamiltonian that describes the dynamics of the system in free condition, and then you put x times f as the interaction Hamiltonian. So the variable x is multiplied by the external force F. This produces energy, and so you put this as the interaction, Hamiltonian interaction into your system. So this response excitation, we consider it both in the frequency domain. Okay. So alpha is the constant that relates the two. So x of omega is equal to alpha of omega times of omega. Okay? The frequency domain, alpha belongs to the complex, is a complex number. Okay? So therefore, we can write alpha as alpha prime, which is the real part, plus I alpha second, which is the complex part. So here, in the filtration dissipation theorem, we do not take the susceptibility as a whole, but we take just the imaginary part of it. And this will make this choice, no, it's not a choice, it's a theorem. This fact gives the name of the theorem as a fluctuation dissipation theorem, because this is the fluctuations, because this is a noise. So we are calculating the power spectral density of the fluctuations of X. And we are going to see soon that this represents the dissipation. The imaginary part of the susceptibility of any system is the dissipation. Now, what is this term? Well, you will see here the Bose-Einstein function, distribution function. This 1/2 comes from the fact that every harmonic oscillator, the fundamental energy is just half h bar omega. Okay. Here we are in full quantum mechanics pictures. So the system is made by a large number of harmonic oscillator, each of them characterized by a frequency omega. Okay, and for each harmonic oscillator, we have the spectrum that starts at half h bar omega, and then there are different levels separated by a full quantity h bar omega. Okay, and so this is the Bose-Einstein distribution function that is like this. Okay. Now, why this is this important part? This is this part of this quantum mechanical part. It's important. It is important because it gives us first a limit when classical physics is no longer applicable, and also it is really important because when omega goes to infinity, this function goes to 0. Okay, and this is reflected, for example, in the black body radiation. If the black body radiation is considered as the thermal noise of the electromagnetic field in the cavity, in the oven, well, we'll see that the spectrum goes to 0 when omega goes to infinity, which is really good. For example, in the equation of Nyquist, this is actually is a really big problem, because the equation of Nyquist, I write it again here. The power spectral density of the noise generator is independent of frequency. So this is not possible in real life, in real physics. So it means that the energy of this generator is infinite. So you can have even at frequency 10 to the 20 hertz, still you have this expression, which is not possible. So when quantum mechanics kicks in, this expression is no longer valid. And so we have to use the full expression of Cullen and Walton, which reassuringly is good, because when omega goes to infinity, this function goes to 0. Okay, so the energy of the total energy of the fluctuations is not infinite. So now let's find the classical limit of this expression. So when we are in the classical physics, well, when h omega is much less than k dt. Okay, in this case, so the average thermal energy is much higher than the quantum energy associated at the harmonic oscillator at frequency omega. Okay, so let's see when. Let's put some numbers in it. So instead of replacing the constants, I have in my mind some fundamental numbers. For example, I know that for a wavelength of 1 micron, we have an energy of the harmonic oscillator of 1.24 electron volts. Okay. And the other numbers that I remember, that when T is 300 Kelvin, then the KBT energy is approximately 1 over 40 electron volts. Okay? So this energy is just H bar omega. Okay? So let's put everything together using these two constants. So H bar omega, this is H times F. So F is the frequency. So let's put it convert in lambda. So F is C divided by lambda. Okay. So this corresponds then to 1.24 electron volts. When lambda is 1 micron, so we can write this 1 micron divided by lambda. Okay. So that's it. And so the KBT, this is 1 over 40 electron volts. Temperature divided by 300 Kelvin. Okay. These are the two equations. So we can convert it. I would like to use it again, the frequency here, because we want to express this in frequency. So what is the frequency corresponding to a wavelength of 1 micron? So the frequency is equal to C divided by lambda, as I said there. So this is 3 10 to the 8 divided by 1 10 to the minus 6. So this is 3 10 to the 14 hertz. So this expression is 1.24 electron volt. And then I have the frequency of this one. So it's frequency divided by 3 to the 14. Okay, hertz. Okay. So now we can put all this calculation together. So what does it mean this? So I have 1.24 electron volt divided by 3.10 to the 14 hertz. And this is a times frequency. Okay, it must be much less than electron volt divided by 40, temperature divided by 300 Kelvin. And so you will see that we are quite safe, actually, because, this is, we can do easy calculations. This is 12 divided by 3 is 4, so this is roughly 0.4. Okay, so here in total we are at 4 10 to the minus 15 electron volt hertz. Okay, electron volt goes away. So here we are at 25 10 to the minus 3 electron volts. So this is 1 over 40. Also, this is 50. Sorry, it's minus 15. Okay. So 2.5 10 to the minus 2. So you will see that at the frequency of a gravitational wave detector, for example, the highest frequency that we can imagine, we can consider this is 10 kilohertz. So we are here 10 to the 4, 10 to the minus 15. So we are 10 to the minus 11. Okay. Here we are at 10 to the minus 2. So even if we go down to 1 Kelvin, the average thermal energy is an order of magnitudes larger than the quantum energy associated at harmonic oscillator at 10 kilohertz. So definitely, for our business of gravitational waves, we can definitely consider the quantum limit. So we can take this limit. Okay, so we are kind of safe. So then, if we consider this in the limits of omega of h bar omega by kBt, that goes to 0. Okay. This is 1 over 2 plus 1 over, well, we can expand the exponential. This is 1 plus the argument, minus 1, so it is the argument. Okay, so this is 1 over 2 plus k dt divided by h bar omega. And then we consider that this is orders of magnitudes larger than h bar omega. So definitely it's much larger than 1 over half. So this is k dt over h bar omega. Okay, great. So then we replace it. So the limit of h bar omega divided by kBt goes to 0 of s x is 2. H bar and h bar goes away, which is kind of nice because it means that quantum mechanics is no longer important in our business. So this is a 2 kBt divided by omega times alpha 7. Okay. So this is the the classical limit of the fluctuation dissipation theorem. And so this is the expression that we are going to use when we want to calculate the thermal noise of in our detector. Okay, now we are going to discuss about some properties of this susceptibility function. Okay, so let's copy here the classical limit of the fluctuation dissipation theorem. Okay. And let's discuss about this. So I said that the definition of the susceptibility function in the frequency domain is that is the function that relates the response to the excitation. So it means that x of omega is alpha of omega times f of omega. Okay. Well, this is a simple function in the frequency domain. In the time domain, this corresponds to something that is a bit more complex. Okay. So in the time domain, okay, so the response of your system is a convolution integral. Okay. So this is a famous theorem of the Fourier transform. The convolution integral is of this sort. Okay. So one requirement that is kind of strong is that this function, this is the impulse. This is called the impulse response of the system. That alpha of t must be real. Okay. So okay, fine. And so alpha of t is related to alpha of omega through the inverse Fourier transform. So alpha of t is the inverse Fourier transform of alpha of omega. Okay. Okay. Let's continue. Let's see what it means. So alpha of t is equal to integral minus infinity to plus infinity alpha of 2 pi f times e to the minus I by f in the f. So written in this way, okay, separating omega from f, you should not use any 2 pi, okay? Because you know, otherwise this is something that is it's a problem when you do Fourier transform. You never know where to put the 2 pi. Instead, if you use a space x and lambda as a two conjugate variable, or time t and frequency f as the two conjugate variable, you never have to remember to take the 2 pi with you. Great. So let's write this in a more explicit form. So this is minus infinity to infinity. So this is alpha prime of omega plus I alpha second of omega. And this is cosine of oh, sorry, this is definitely st omega t plus I sine of omega t in the f. Okay. So now, if I want this real, two conditions need to be fulfilled. The two conditions is that this integral must be 0. Okay. So the integral of alpha prime omega time sine of omega t df, this must be 0. And the other is this integral must be 0. So alpha second of omega time cosine of omega t df is equal to 0. Okay. Okay, great. So it means, so I erase this. It means that this needs to be a pair function with respect to omega, and this to be an odd function. So it means that alpha prime of minus omega must be equal to plus alpha prime of omega. So in this case, this integral that goes to minus infinity to plus infinity definitely 0. And the other one, which is matters most to us, is the consideration on alpha second. Alpha second of minus omega. This must be an odd function. Okay, great. So that's it. So we can remove it. So these are quite important condition on our function. So it means that now on we can consider only the positive, only the positive part of the spectrum. Okay, because wait a moment. This is alpha prime was multiplied by sine. Okay, and this was multiplied by cosine. Okay, yes. So we can consider just the positive part. So we can move from this expression to considering only omega positive. So we have the expression of Sxx is equal to 4k dt divided by omega times alpha second of omega. Okay? Great. Now, let's move to another property of alpha omega that actually it justifies the name, gives the name of the theorem, fluctuation dissipation theorem, because we need to demonstrate that with alpha second, we can calculate the dissipation of our system. Okay, so let's do it. Imagine that we have our system. X is an observable. Okay. We want to calculate the work done by the excitation, the external excitation, on a cycle. Okay, consider we are in the frequency domain. So we do the harmonic analysis of our system. So we imagine to excite the system with a harmonic force, and the response will be harmonic. And so we are going to calculate which is the energy after one cycle of excitation. If the energy is preserved, after one cycle, the integral must be 0. Okay? Let's see the result of it. So we go to calculate the energy. We go through the power. So the energy in one cycle is the integral from 0 to t. T is a period of the cycle of the instantaneous power dt. Okay. So the instantaneous power is the force time. So the force times dt. Okay. Fine. So the force is the external excitation. V is the speed. We know the response. So the force is F naught, real part of e to the I omega t. Okay, this is the excitation. So the response, x of t is F naught times alpha. Okay, so better to write in this way. So the real part of alpha of omega t. Okay, so the real part of alpha, which is a complex number, times F naught times e to the I omega t. Okay, and the speed, which is the derivative of t, this is a I omega, the real part I omega alpha F naught e to the I omega t. Okay, so let's put the things together if it's possible. We need to express this this integral. So the energy after one period is the integral 0 to t. The force, so this is F naught times the real part of e to the I omega t times the real part of I omega alpha F0 e to the I omega t. Okay? So let's erase all of this. Hopefully, I'm going to end up with an easy integral here. So F0 is the amplitude of the force, is real, so we can take everything out. So this is F0 squared. And then we have the integral. So this real part, well, it will have a factor of 2 here and a factor of 2 there. So this is a factor of 4. So the first is e to the I omega t plus e to the minus I omega t. And then I have here times I omega alpha e to the minus plus I omega t. And then plus the complex conjugate. So it's minus I omega alpha complex conjugate e to the minus I omega t. Okay? Perfect. So let's see what is the result of it. So let's calculate first the product of the two parentheses like this. So I have some DC terms. For example, when I multiply this by this, the time dependence goes away. So this is a minus I omega alpha complex conjugate when I multiply this by this. And then also when I multiply this by this, the time dependence goes away. So this is a plus I omega alpha. Okay? And then I have terms that depends on 2 omega and minus 2 omega. So plus I omega alpha e to the 2 I omega t minus I omega alpha star e to the minus 2 e omega. Now, it is easy to see that when we integrate in one period, these functions are periodic. So this function will give 0 to the integral. Okay? They go away. This is instead independent of time. So therefore, we put this result in there or in there. So the energy in one period is F naught squared divided by 4. Then this is this goes out of the integral. So this is I omega alpha minus I omega alpha complex conjugate. And then the integral from 0 to t in dt is just the period t. Okay? That's fine. So let's analyze what is in there. So, well, we could take out omega out of, okay? And this is nicely, this produces a 2 pi, something that is independent of omega, okay? And then I have I alpha minus I alpha star. So I alpha minus I alpha star is equal to I alpha prime plus I alpha second minus I alpha prime minus I alpha second. Okay. So this part and this part go away. These parts go away. Then I have I times I is minus 1. This becomes plus. minus 1. So this is minus 2 alpha second. Okay, so therefore, we are going to have a very nice result. So this is produced 2 pi. This is minus 2 alpha second, so the result is minus 2 and 2 cancel with 4. So f0 squared alpha second. Okay. So after long calculations that seems quite difficult, the result is rather simple. So the energy produced by the external force after one period is negative. So it means that the work done by this force is negative. So it dissipated. The positive work done by the external force is less than the negative work, okay? And it is proportional to the force squared, and is proportional to the alpha second, okay? So the imaginary part of the response function of the system. So this is a kind of remarkable result. So let's write it here. So we call it the work, okay? The work is the modulus of the energy in one cycle. So this is f0 squared times alpha second, okay? So this is kind of nice because maybe Professor Reed will tell you in the following lecture that one of the most important way to calculate thermal noise on mirrors is to use not directly the fluctuation dissipation theorem, but to use the Levin equation. Well, the Levin equation is exactly this. Because instead of calculating directly the response function of your system, you copy this, and then so well there. So you express your noise, the power spectrum density of noise of the variable x as 4kBt divided by omega, and instead of alpha second, you just write this as the work done, the dissipation done by the external force divided by the amplitude squared of the external force itself. So practically, we take the system, we force, and we can use a finite element analysis to do this. So we impose the force, we deform the system, we calculate the dissipated energy, and then we divide it simply by the force, okay? In a minute, I'll show you how to calculate the dissipated energy through this technique. So this is it's called the Levin equation. okay, which is rather important for the calculation of thermal mass. Okay, great. So let's move to another subject. So we are getting there. Next, I'm going to talk about what is the expression, the general expression of alpha. Okay, now continuing to talking about properties of alpha second. So let's see another aspect that is quite important, okay, especially for those of you who work on thermal noise. There is a general expression of alpha second, okay, and that is valid in all the systems, especially for mechanical systems, okay? So the expression is this one. Alpha second is I'll give you the expression, then we make a comment. Is always made by three elements. So the first of these elements is the most intuitive one. Alpha represents the susceptibility. So susceptibility is the property or the characteristic of the system to yield after the excitation. So alpha is big when the system is soft. Okay. So therefore, here at the denominator, you always have something that gives you the rigidity of your system. Okay. This is very important because this is a very intuitive, because it is based on the definition of susceptibility. Then at the numerator, you have something that expresses the imaginary part of the response function. And the imaginary part is written, this is not intuitive at all, it is written always as the product of two quantities that are rather important. One is called dilution times the other quantity is what is called the loss angle phi. Okay? And although it's not so important to talk about the rigidity, because the rigidity now you know what rigidity is. If alpha, the dimension of alpha, this is the response divided by excitation. This is a meter in mechanics. Okay, this is mechanics. Meter per Newton. Well, the rigidity is the opposite. Is Newton per meter. So, okay, represent how rigid is the system. So if you deform the system by 1 micron, how many Newton you need to apply? Okay. It means that both dilution and the loss angle the dimensions are 0. Okay, they have no dimension. So these are a-dimensional number. Okay, so let's talk about what is the dilution and the loss angle. So I'll erase this. And let's imagine to that. So we invent a system. Okay. So let's take a cylinder like this. Okay, of length L and surface S. The system is characterized by a Young modulus E. Okay. The observable we choose as observable actually the length of the cylinder. So the length of the cylinder is not a constant due to the fact that there is thermal noise. Okay, so the length of the system of the cylinder is a function of time. So this is L plus the variable x. Okay, great. So now this is a very important part of the calculation of thermal noise, because we specify which is our observable. So our observable is the length of the cylinder. Okay. Second step is, once the observable is specified, we need to associate the quantity, which is the excitation, okay, of the observable, the conjugate quantity. And so we have to remember that the conjugate quantity need to form energy when multiplied by our observable. This is kind of easy on mechanics. This is a displacement. So the conjugate quantity is a force, okay? So it's kind of easy, and the force is, or we should imagine a force applied to both ends, okay? So in this case, the center of mass remains fixed, and so this is the force, and so we can study the dynamics of it. And we do the dynamics at the beginning in a very simple way. We do not consider the mass, okay? So we consider just this body as made by just the elastic part. So the length is kind of easy, the expression of it, because, well, this is definitely is proportional to the force, okay? And then we have to divide by the elastic constant of the system. So P divided by, this is the Young modulus, times the surface divided by the length, okay? So this is L divided by E times S. Okay, that's fine. Now you can imagine that in this system, uh, the response, by definition, is alpha times f in the frequency domain. So okay, so in the frequency domain, we can consider that this force is harmonic. There will be an harmonic response. Well, alpha, immediately you recognize what alpha is constant with frequency, and it is exactly this. On top of it, this belongs to the real numbers. So it means that alpha second is equal to 0. This system does not exhibit any thermal noise. Okay? Because here the response function is perfectly real, and so there is no possibility to have thermal noise out of the system. So now we have to think how is possible that the response function, at least in the frequency domain, is not real, but has associated an imaginary part. So the way how we do it is to consider what's happening in the real world. In the real world, this relation is not true. This relation is not true, not at all. It is not true that immediately when we apply a force F, the length of our system changes immediately, okay? And it is not related to some fancy consideration based on special relativity. Special relativity, we know that nothing goes faster than light, so definitely the response of the system cannot be instantaneous. No. It's not related to that. It is related to the fact that the response of the material, which is exactly represented by the Young modulus, is the result of complex mechanism involving the interaction between the atoms that are inside the cylinder. So it also means that when we apply a force on the two extremes of the cylinders, there is an immediate reaction to the system. So the system shrinks. For example, if the force are in this direction, it shrinks immediately, but then it continues to yield because the material relaxes. And if it is hard to think why there is a relaxation, I'll give you one of the mechanisms, okay? That is kind of, for me, is kind of intuitive, but maybe for you is not intuitive. When you compress the material, it's easy to imagine that this material heats up because you compress the material, okay? Imagine air, you compress air, the temperature goes up, okay? So normally when we make some work on a material, this is not always the same, okay? When we make the work on the material, the temperature goes up, okay? Fine. So when you compress the material is more rigid because there is thermal expansion. So there is elasticity plus thermal expansion. But then you wait a bit and the temperature goes back to the original value. So when the temperature decreases, well, the material relaxes, and so you can compress even further because the temperature decreases. So the thermal expansion gets in, and so you have you have an evolution of the response of your function. This is the reason why this relation, this simple relation, is not real. Any response of a real material, could be thermal response, mechanical response, electrical response, cannot be instantaneous. They have what is called, they goes through a relaxation process. Always, this cannot be avoided. So therefore, we cannot write the function like it is in this way. So we have to introduce a convolution interval. But I would not apply the convolution interval to this function, but rather to the opposite. I'll show you. The opposite function is this one. F of t, it's equal to E times S over L times x of t. Okay? Well, in this case, I cannot write this in this way. And I have to write it in that way. So S over L is a constant that can be taken out. Okay? So it's an integral 0 to t. Actually, this is a minus infinity to t. E t minus s times x of s ds. Okay? So the Young modulus is not constant. The Young modulus is something that is of that sort. Is of that sort. For example, if we take this is time, and x is of this sort. Okay, for example, we put a step function on it. So this is x. The Young modulus is of that sort. So not the Young modulus, the force, well, in this case, the force is considered as a response, is of that sort. There is an immediate, instantaneous response of the system, and then the system becomes a bit softer. So to obtain the same displacement, you need less force. Okay, and so this is x of t. Okay, so what is the E, the fundamental? Well, since this is not exactly, this is something different from the Young modulus itself, because you see the Young modulus is like the integral in time of this function. Let's call it this E small e. Okay, and the integral will give the Young modulus E itself. So in this case, it's easy to demonstrate that the function E of t is practically the time derivative, okay, of this function force, and then we reconvert so we take this L over S. function force times L over S. Okay, so practically this will be L over S. L over S is not so important. Times, well, the derivative is a delta function. Okay, and this is it represents the immediate response of the material plus, okay, something here, let's call it eta, which represent the relaxation of the material, okay, and is thanks to this relaxation, that the Young modulus, or the integral of this function, produce a Young modulus that in the frequency domain has a real part and an imaginary part. And the imaginary part enters into the imaginary part of the response of your system. And here we have the origin of thermal noise and the way how we calculate the thermal noise in the mechanical system. Now it's time to introduce one of the main actors of the thermal noise calculations in gravitational wave detectors, which is the loss angle, okay? So let's restart from this general expression. So I want to remark this fact that this can be written as K, like a spring constant, times x of t. This is no longer true, but in reality, we should write this as a convolution integral. So this is like an integral minus infinity time t, function, I invent function eta, t minus s times x of s. Yes. So it means that when we go from the time domain to the frequency domain, so this goes to f of omega, then we have the Fourier transform of the function eta. So this is can be written copying the expression, this expression. So this can be written in k of omega times x of omega. Okay. And well, there are two expressions. So first expression is a k prime of omega plus I k second of omega. Okay, real imaginary part. Okay, or it can be written in that way. So modulus of k of omega times e to the I phi of omega times x of omega. Okay, and this is what is called the loss angle. Okay, because when this angle is not zero, the external force produces a work that is negative after each cycle. So practically, the external work is dissipated inside the material. In practical terms, at every cycle, some work done by external force is transformed into heat that is heating up the material. Okay, it's a tiny fraction, but that's it. This is what's happening. So in most of the practical cases, this loss angle is kind of tiny, is at most 10 to the minus 3. Okay, so therefore there is a, as you may expect, there is a simpler expression of the response, which is this one. So f of omega is k of omega 1 plus I phi of omega. Okay, and so said I of omega goes from, well, the smallest phi ever measured are of the order of 10 to the minus 10. And then here, yes, indeed, you can have a phi that is really large, but in the material that we use, you can consider that phi is 10 to the minus 3 at most. Okay, sometimes it's a bit more than 10 to the minus 3, but okay, this is roughly the range. So definitely the approximation of the exponential is perfectly justified. So let's see now how to calculate the thermal noise of a bar like this related to the length, okay? And I'll show you how to do it immediately. So let's rewrite all the equations. So no longer we have a Young modulus constant like this, but the Young modulus is now an E0 1 plus I phi. Okay, because there is a relaxation inside the material. So therefore, the equivalent spring constant is the Young modulus times S by L. So this is S by L times the Young modulus 1 plus I phi. Okay. That's great. So the power spectral density of the length, okay, a single side. So considering the frequency just positive, so it's 4 kBt divided by omega. This is the residual of the quantum origin of this of the fluctuation dissipation theorem times alpha second. So alpha is the response. So the response is the length divided by the force. Okay. So therefore, the length. So we call it x. No, that's fine. So therefore, we consider that the force is 0 times cosine of omega t, which is 0 times the real part of t. Okay, and So f of omega is just f0. Or f0 times delta omega minus omega 0. Omega 0 there. And then the length, okay, is a response to it. This is a f0 divided by the spring constant. So is S by L, E0, 1 plus I phi. Okay, delta omega minus omega 0. Right. So the response, which is L over F, is simply, so alpha the response is L divided by S times E0, 1 plus I phi. Okay, which is roughly, because we can use the fact that phi is rather small. So L divided by S E0, 1 minus I phi. Now we can see clearly which is the real and imaginary part of the response function. Okay, so let's progress. I remove this. I remove this. And so is it true that alpha, so now this is alpha prime plus I alpha second, and alpha second is minus L phi divided by S E0. Is it true that this is dilution times phi divided by rigidity? Yes, it is. In this case, dilution is exactly 1. There is no expression. And maybe now you understand, well, later on it will be much clearer. But the dilution function is telling us where the dissipation occurs. In this case, the material is homogeneous, okay? So when we apply the force, we apply a strain everywhere in the material is homogeneous, the dissipation occurs everywhere in the material in the same way. So therefore, the dilution here is just 1, okay? Then we have the loss angle. So the loss angle is the imaginary part of the Young modulus that comes from the relaxation that are happening inside the material. And then there's the rigidity. And the rigidity, clearly you can see that is the rigidity is the cross-section of the body and the Young modulus, the constant part of the modulus of the Young modulus, divided by the length. Okay? If you want to decrease the rigidity, so in order to make the thermal noise higher, we need to have a really long beam and really thin. In this case, the thermal noise increases, okay? The opposite, so thick and short beam, this corresponds to a system that is quite high in the rigidity, so low in thermal noise. And in fact, this is one of the reasons why the mirrors of gravitational wave detectors have the shape like that way, because if they are really thin and long, the thermal noise is kind of large. And so you need to have a really a system that has a large surface, large surface and minimal length. The reason why the mirrors keep a certain thickness is because in this simple calculation, we are not considering the flipping modes, okay? So for longitudinal deformation, better to have a length that is 0. But when the length goes down considerably, well, there are other modes that are possible to excite. And these modes are becoming really, really soft, okay? So for complex expression of thermal noise, this these modes appears, and so they take the majority, the all thermal noise contribution. So, okay. So then you can see here what is in this case the dilution and the rigidity. Let's continue on the calculation. So therefore here SLL of omega is equal to 4 kBT divided by omega times S E0 divided by L times phi. Now, there is a little details here is the sign, okay? Here you can see that the sign is negative, so it should be there a negative. So with negative, this is kind of problematic unless the loss angle is negative. So here the sign depends on the convention on that we adopt for the Fourier transform, okay? And then there are another requirements that is really important is that after one cycle, the energy can only be dissipated and not created, okay? So the sign of alpha second depends strictly on the convention that we use for the Fourier transform or the anti-Fourier transform, and on the fact that is really a physical requirement that the energy is effectively dissipated and not created. So therefore, in order to cut down the problem we just take phi as positive and with no negative sign on it, okay? So it's not a problem. So therefore, you will see here immediately that you have nothing more to do. This is the expression of power spectral density of the thermal noise related to the length variation of a cylinder. And it's nice to see that this corresponds exactly to one of the to the thermal noise of mirror, because we take the square root of it, okay? So we call it what is called the amplitude spectral density. This is a meter per square root of hertz. Okay, this is omega. So this is a square root of 4 kBT, the cross section, the Young modulus, divided by times the loss angle, divided by L times omega. And so if we plot this in log of frequency and log of SLL, okay, so this is exactly F21 over 2, okay? Thanks to this fundamental frequency dependence that is inside the theorem, the fluctuation dissipation theorem. In this case, we consider that the loss angle is perfectly a constant, but sometimes it's not. Sometimes it's not a constant. So therefore, when it's not a constant, on this general shape of 1 over square root of f, you might have other dependence that these are related to the square root of how the loss angle behaves with the frequency. Okay. So now you understand a bit better the how to calculate it. Okay. Professor Reed will tell you really the general expression of the thermal noise coming from test masses, a mirror, and it's really complicated because they are all the elastic constant of dimension of the test masses and the coatings. Okay. Now let's move to a system that is a bit more complicated than this. So a system that is made with well, practically it's the same system, but we attach at the end of it a mass, because here the mass is not contemplated. We have just the elastic part of the system. But when we have the mass, we enter into the normal domain of a harmonic oscillator. So now the next subject is how to calculate the thermal noise of an harmonic oscillator. Okay. Thermal noise of an harmonic oscillator. Okay. So, oops. Okay. Now, the system is kind of simple model. So we have n a spin constant x. So we have k, sorry, and we have the displacement x. And we are interested to calculate the power spectral density of the fluctuations on the position of the mass m along x. Okay. So how to do it? Well, we need to go through alpha. So the response. Okay. So therefore, we have to force the system with something that excite the system, and the product x times this quantity that excite the system is an energy. So in this case, it's just simply a force F. Okay. The dynamics is rather simple. So m x double dot is acceleration. This is it is equal to k times x. Okay, with a negative sign, because this is the restoring force, plus the external force F. This is in the time domain. In the frequency domain, this is minus m omega squared times x is equal to minus k times x plus f. Okay? So we have to calculate the response. So the response alpha is the function, the response function is the response divided by the excitation. So this is after calculation, this is a 1 divided by, so we take the x we put there, so it's k minus m omega squared. So as the thing stands, so this is a alpha prime plus I alpha second, and we will see that there is no imaginary part, there is no thermal noise. Okay, there is no dissipation, no thermal noise. This is not true because we know that the spring constant of a real system, the spring constant, we have seen that is the Young modulus times the cross-section of your material divided by the length, okay? In this case, the Young modulus is not constant. It is something that undergoes to relaxations, okay? So the Young modulus is made by, in the frequency domain, by a delta function, okay? Is immediate response, plus something that is related to relaxation. So it means that here, this can be written as a k naught 1 plus I phi, okay, in the frequency domain. So we are going to use this expression. So this is 1 over k naught 1 plus I phi minus m omega squared. And so now we are able to work out which is the imaginary part and the real part, the real and imaginary part. We are interested just in the imaginary part, so let's do it immediately. Let's see if there is. Yes, okay. The imaginary part is minus k naught times phi divided by k naught minus m omega squared plus k naught squared phi squared. Okay, I just multiplied it and divided by the complex conjugate of the denominator. And so the complex conjugate has is proportional to k naught times phi with a negative sign. So therefore, the real part is, the imaginary part is just this. Okay, so now I apply the fluctuation dissipation theorem in the limit or in the classical limit. So I erase all this. So S L L, sorry, XX is 4kBT divided by omega times alpha second. We take just, okay, either we consider phi negative or we take just the modulus of it. So this is 4kBT divided by omega, k naught times phi divided by K naught minus M omega squared plus K naught squared times phi squared. So here it is. Maybe it's worth writing it there, because later on we're going to plot it. Okay, fine. So I erase it, everything. So let's see if let's see what are the different components. Oh, sorry. Okay. What are the different components? So here again, the dilution factor is again 1. There is no the dissipation inside the material is everywhere. Okay. The rigidity is exactly, so the rigidity is exactly equal to this number. So is the inverse of it. So the rigidity is 1 over K naught times okay, times 1 minus omega divided by omega 0 squared plus phi squared. Okay, this is the rigidity of the system. And the rigidity of the system is kind of this sort. So if we want to plot the rigidity as a function of omega, so there is a let's call it a constant value 1 over K naught. Okay, the larger K naught, the larger. So wait a moment. Where is the inverse? So K naught. So the larger K naught, the larger the rigidity, because it's exactly the opposite. Okay. And then at very low frequency, well, omega over omega naught is the resonant frequency, is negligible compared to 1. Phi squared is at least 10 to the minus 6. Okay. So therefore, at low frequency, the rigidity is exactly K naught. Then what's happening is that when omega increases, this number becomes less and less important. When omega is equal to omega naught, the rigidity, this part drops to 0, and the rigidity is only given by the loss angle of the material. This is when, in fact, at the resonance, the inertia is fully compensated by the elasticity. The two effects cancel out, and what is left is just the dissipation. So when we increase the frequency, the rigidity goes down to this minimal level. So this is K naught times phi squared. Okay. Yes, fine. And then we go over, omega goes over omega naught. So this is exactly omega naught. And then when omega is above omega naught, this number becomes, this square becomes positive, and it becomes greater and greater. So it becomes greater and greater. And then we have, okay, the function that is like this. So is a square function. This goes like omega squared. It's proportional to omega squared. Okay? So this is the rigidity. So what does it mean from the point of view of thermal noise? Immediately looking at the rigidity, we know that, okay, at low frequency, the thermal noise is at a certain level, okay? Then the thermal noise becomes larger because the rigidity goes down. And then at high frequency, the thermal noise is becoming less and less evident because the rigidity goes increases up to infinity. The reason why the rigidity goes increases so much is because it's the effect of the inertia. No, the system doesn't want to move when the frequency of the force is really high. Okay, because there is inertia. Okay, great. So now, what is the expression of the thermal noise? Well, it is exactly the same. In this case, we consider phi completely constant. So therefore, we can just plot the square root of s x x, and well, let's plot the logarithm of it because it's much simpler here. The logarithm of frequency. So it is something like this. So at the low frequency, so this corresponds to F naught. At low frequency, when the rigidity is constant, the frequency dependence is given by this 1 over omega. So we plot the square root of it. So this is like F1 over half. Okay. At the resonant frequency, we have the maximum of thermal noise because the rigidity is 0. And then for frequency above the thermal noise, well, look at the power of omega. This is omega to the 4th, omega to the 5th square root. So this is f to the minus 5 over 2. Okay. And so this is the general behavior of the thermal noise of a simple harmonic oscillator. Okay, so this is quite good. The harmonic oscillator also gives us the opportunity to discuss two other details of the physics that is in it. So the two other details is or quantities is one is the the quality factor, and the other is the decay constant. Okay, so I erase all this. And I go quite fast on it because now I think that I see that we are well beyond the 1 hour, which is the limit of this lecture. So the quality factor Q has two meanings. The first, the quality factor Q of a resonance is the frequency of the resonance divided by what is called the width of the resonance. So when we say the width is, we should plot the response, okay? So we should plot the response. The response is the function x, is a function of frequency. And so this is a, goes to 0. And you calculate the width as the amplitude at the width at half maximum. So this is a delta f. So this is f naught. So the ratio of f naught divided by delta f is the quality factor of the resonance. This has also another definition, the quality factor, a definition on energy, and this is 2 pi. The dissipated energy, well, 2 pi, the stored energy, divided by the dissipated energy on one period. Okay? So quality factor is a physical quantity that is really well known, and is a fundamental when we discuss about resonances. So as a matter of fact, so let's relate the quality factor to the loss angle, okay? The quality factor to the loss angle is, so this is simply 1 over the loss angle at the frequency of the resonance. Okay, and this is kind of nice. It's a simple relation, and in fact, sometimes in some textbook or articles, the loss angle is written as q to the minus 1. Okay, it's kind of important to say when you read the literature. Okay, great. Now this is the damped harmonic oscillator in the frequency domain. In the time domain, we can have another phenomena, like for example, this is time. So we excite the system and we let the system oscillate. And we see that the oscillation are damped, okay, following an exponential law. So this is the x, so x of t is initial amplitude A naught, e to the I, sorry, to the minus t over tau. Okay, so this is the, this is the amplitude times, well, cosinus of 2 pi f naught times t plus an initial angle theta. Okay, this is the amplitude. This is the envelope. Okay, the envelope follows an exponential law. And so this is a tau is the decay constant of the harmonic oscillator. Well, if we consider an harmonic oscillator, really simple, made by one type of material, okay, like this, and there is no other forces apart the elastic forces inside the material, then the material is characterized by the loss angle phi that is related to the Young modulus. So the decay time, okay, the decay time is pi times f naught times the quality factor of your system, or following what we have seen before, pi no, sorry. So the quality factor of your system is pi f naught times tau. Okay, so this is a-dimensional. Okay, and so the loss angle is 1 over pi f naught times tau. Okay, so the longer the decay time constant is, the higher the quality factor, and the smaller is the loss angle. Okay. Right. Okay. This is a rather important aspect of the dissipation inside the material. And now let's move to another topic that is the calculation of the thermal noise of a pendulum, and why is slightly different from the calculation of thermal noise of a simple harmonic oscillator.